This analysis studies the biomechanics of the basketball three-point shot whilst comparing the movement and technique of NBA legend Klay Thompson to that of a student athlete. The performance is broken down into three key phases: preparation, execution, and follow-through, with focus on joint actions, muscle group involvement, and position. The analysis also evaluates the influence of stability and balance on the performance efficiency. As seen, the preparation phase begins in the athletic stance shown by both athletes. In this position, their center of mass is over the hip joints, creating balance and a solid base and therefore position. The ball is held close to the body to help stability and reduce rotational error. Key joint actions include the dorsiflexion at the ankle, flexation of the knees, hips, shoulders, elbows, and wrists. Primary muscle groups activated in this phase include quadriceps, hamstrings, glutes, deltoids, biceps, and wrist flexors. The core stabilizes and supports alignment throughout the body. In the student athlete's performance, the presence of a valgus moment is observed at the knees, where the inwards collapse of the knee joint reduces stability and therefore will impact force generation. Thompson maintains optimal alignment with symmetrical joint positioning and consistent posture control. This is a critical inefficiency, as the valgus moment not only compromises knee joints, but also disrupts proper alignment for effective force summation throughout the lower body limbs. Without stable knee tracking, the student athlete is unable to produce and transfer maximal force. The execution phase consists of the application of force and movement throughout the kinetic chain. Both athletes move from the ground up through the feet, up the legs, through the torso, down the arms, and through the fingers. This begins with the triple extension of the ankle, knee, and hip joints, contributing to vertical lift and power output simultaneously. Flexion and subsequent extension of the shoulders, elbow, and wrist occur. In Thompson's shot, the wrist flexors, which are preloaded with elastic potential energy, release this energy through a controlled wrist flick to generate backspin and velocity. This movement also demonstrates the application of Newton's third law of motion. For every action, there is an equal and opposite reaction. The movement also relies on the momentum transfer throughout the body, with greater momentum in Thompson's performance due to higher coordination of body parts. Throughout the shooting motion, the body utilizes several third-class levers to generate speed and control. At the shoulder, elbow, and wrist joints, the force is applied between the axes of rotation and resistance, allowing for faster coordinated movements. These lever systems favor velocity over force, making them biomechanically better for a skill such as a jump shot, where rapid arm extension and precision are critical. Thompson demonstrates efficient lever use throughout the full extension and time sequencing, while the student shows reduced range and incomplete elbow and wrist flexion. Within the final part of the three key phases, the follow-through, emphasis is placed on the athlete's release mechanics and body control during the final stages of the jump shot. The ball is released at the highest point of the jump, optimizing the height and release and allowing for greater clearance over defenders. This position also enhances the angle and arc of the shot, increasing the chance of success. Thompson, at his peak, has an elbow angle of 107 degrees and a strong loaded wrist with an angle of 95 degrees. This final moment before the shot is released shows how perfect form generates ideal backspin, contributing to both accuracy and soft landing of the ball on the ring. In contrast, the student's peak is very different. In several observed attempts, elbow angle is 75 degrees and wrist angle when cocked back is very limited at 175 degrees, reducing backspin. The lack of wrist flexion diminishes the efficiency of energy transfer from upper limbs and compromises the ball's rotational control in flight. This difference in joint positioning reflects broader issues in the summation of force and coordination of the student athlete. Thompson demonstrates refined sequencing throughout the kinetic chain, beginning with lower body extensions and concluding with a fluid upper body release. The student athlete initiates the shot prematurely with the arms bypassing lower body contribution and disrupting the momentum pathway. As a result, the generated force is insufficient and the projectile lacks velocity and consistency to reach the ring. Technique along with posture control during the release also differs. Thompson is refined technically and has perfect execution with his shoulders stacked over his hips and both feet are facing the ring and landing symmetrically. His shooting motion is compact and direct, with the ball following a straight line path from the shooting pocket to the release point. In contrast, the student athlete's technique reveals several biomechanical inefficiencies. The right foot rotates inwards, compromising stability and reducing the base of support. Additionally, the ball crosses the midline of the body during the shot, disrupting linear force application and potentially affecting shot accuracy. These deviations from optimal shooting form indicate reduced coordination and alignment throughout the body. Newton's first law of motion explains how an object remains at rest unless acted upon by an external force. This is observed in the initial stages of the shooting motion. Thompson is able to overcome initial inertia effectively due to a strong, balanced, athletic stance and coordinated muscle loading across the lower body. His grounded position and muscular engagement allow for a rapid transition from static to dynamic movement. This matters because the quicker an athlete can overcome inertia, the faster they can generate force and begin a movement sequence. This is essential for achieving rhythm and further game contexts. Newton's second law of motion, also known as F equals ma, further explains this gap in biomechanical principle understanding between athletes. Thompson's longer lower limbs and greater degree of knee flexion, coming in at 104 degrees and 103 degrees, during the preparatory phase providing a larger range of motion over which force can be applied. This increases the time and distance available for muscle contraction, enhancing both force output and acceleration. The student athlete doesn't bend his knees as much, coming in at 106 degrees and 113 degrees, and therefore lacks this efficiency and power output to reach the required velocity. This directly affects how the student performs. Since he doesn't bend his knees enough before the shot, he can't push off the ground with as much force or through a full range of motion. Newton's second law explains this pretty clearly. Less force means slower acceleration, which shows up in how the ball moves. This explanation is why he only made 2 out of 10 three-pointers, whilst Thompson nailed all 10 of his shots from long range. Newton's third law can also help explain this. Thompson applies a greater downward force into the ground, which generates a greater ground reaction force in return. This upward force assists in liftoff and contributions to the overall energy transfer in the shot. In contrast, the student athlete's reduced lower body engagement limits the magnitude of this reactive force, leading to a weaker jump and therefore a lower release, reducing arc and chance of a successful bucket. Thompson also displays superior force summation. As seen, our student athlete moves his upper body before activating his lower half, while Thompson begins with powerful activation of the large muscles including glutes and quads. This force travels upward through the core and continues into small muscles of the shoulders, arms, and wrists. Each segment contributes to building and transferring energy towards the release point. This matters because proper force summation ensures maximum energy is transferred through each body segment, resulting in a more powerful, coordinated, and consistent shot. Therefore, poor sequencing, as seen in student athlete, leads to take energy leaks, reduced shot velocity, and a lower chance of scoring from long range. These biomechanical advantages are supported by timing and joint data. Thompson completes the shot in 0.67 seconds compared to the student athlete's 0.73 seconds. A shorter time to release reflects a more explosive movement in a shorter amount of time. Upper limb mechanics further impact velocity. Thompson at his peak has a right arm elbow angle of 107 degrees. After releasing the ball, the same joint ends at 150 degrees, whilst the student athlete's peak is 76 degrees and post-release is 164 degrees. This means Thompson uses his angles more efficiently. Bigger is not better in this case. Peak should be no less than 95 degrees, and post-release angle differs upon the person. The combination of these upper limb differences contributes to a more explosive, coordinated, and biomechanically efficient release from Thompson. Once the basketball leaves the shooter's hand, its success to make it to the hoop is somewhat determined by the efficiency of its flight path. The biggest biomechanical variables in this phase are the release angle, release speed, and release height, all of which are made by the athlete's form and technique during the shot. These variables, along with the external ones including gravity and air resistance, determine the shape of the ball's parabolic trajectory. At 6 foot 5 inches, Klay Thompson's technique results in an optimal release angle of 55 degrees, combined with a high release point due to his vertical leap and long levers. This produces a smooth, upward arc that allows the ball to descend into the hoop at a steep angle. For a student athlete at only 6 feet tall, optimal arc should be closer to 55 to 60 degrees, but the student athlete's shorter limb length and poor form led to a flatter release angle of 40 degrees, reducing the shot arc. Backspin created through wrist flexion at the point of release is possibly the most critical part of the flight behavior. Thompson generates significant backspin due to a wrist angle of 95 degrees, contributing to shot stability through the air. This is explained by the Magnus effect, where the spinning motion produces a small upward lift and stabilizes the ball's flight. In contrast, the student athlete's wrist angle of 175 degrees reflects minimal flexion, limiting backspin. This just means that with less rotational control, reducing the chance of the straight shot and the far distance needed to make a shot. Gravity as well as air resistance always have an effect on both the players and the ball. Firstly, gravity is affecting everything, pulling it towards the earth at 9.8 meters per second, therefore pulling the ball downward from its highest point or at the peak of its arc. However, Thompson has gravity working in his favor, as his optimal angle for release is much greater than the student athlete's, pulling the ball right through the hoop, whereas the student athlete's lower release point reduces the vertical drop and increases the angle at which the ball must enter the hoop, narrowing the margin for success. Air resistance is mostly negligible in these situations, but as the student athlete is outside, wind and other external factors may affect shot path. The curve of the shot is the final observation expression of these biomechanical variables. Thompson's high arc, smooth backspin, and centered follow-through is a result of consistent parabolic shot curve. The student athlete's flat arc, lack of wrist flexion, and inconsistent release path in a more direct trajectory lacks the same control and forgiveness. In summary, the flight path of the basketball is determined by the athlete's application of biomechanical principles during the release. Klay Thompson's shot shows how optimal release angles, backspin, vertical lift, and body control combine to create a reliable and efficient projectile trajectory. Whilst the student athlete's performance shows developing mechanics but lacks angular precision, spin generation, and vertical positioning needed to consistently replicate an ideal flight path.